Hello, Gen Chem friends. Hope you're doing well today. So all of the gas law calculations we have done so far in this chapter, and we have admittedly done a lot of them with a lot of different equations, all of them have as their foundation the kinetic molecular theory. That theory is essentially a model that explains or seeks to explain gas behavior in a particular environment. Now, there are several postulates to the kinetic molecular theory that I have on subsequent slides in Canvas. I'm not going to go through those here. You should go ahead and read those and know those postulates. For right now, what I want to focus on is the kinetic molecular theory, and in particular, its relationship to this concept of ideal versus non-ideal gases. Because all of the gases we have dealt with so far, be it pure substances or mixtures or gases generated as part of a chemical reaction, all of those we have assumed to be ideal gases. What that means is that we have assumed that those gases, when they are in their respective container, we have assumed that the interactions between particles, between gas molecules, is insignificant, and that their size is small compared to the space in between molecules. With those two assumptions, that states that basically the volume of the gas particles is essentially the volume of the container, and that the majority of the interactions that happen in a sample of gas molecules are between the gas molecule and the sides of the wall of the container. Okay. In ideal gas conditions, any interactions that happen between gas molecules are insignificant. And it turns out that assuming that a gas obeys ideal conditions, assuming that a gas has those two properties, that's a pretty good assumption to make, because those conditions are generally at high temperatures and low pressures. And when we say high temperature and low pressure, we mean something that is around room temperature, and low pressure something about around atmospheric conditions. Okay. So it turns out that those assumptions about particle size and interactions between particles, that is reasonable. And so most gases behave ideally. And we can use the ideal gas law and those associated equations to calculate specific parameters about that gas. Where things get a little sketchy, where things get a little more complicated, is if you have a gas that is at non-ideal conditions. Particularly, this is at temperatures that are very low or at pressures that are very high, because it's with both or with either of those conditions that the gas molecules start to slow down. And when they slow down, there is more chance for intermolecular interactions to occur between gas molecules. And those can be significant at low temperatures and high pressures. Also, at those conditions, we also say that the particle size is significant compared to the space between particles. Because if those molecules are slowing down, then the space in between them gets smaller. So, those are the two stipulations of non-ideal gas conditions that you should know. And so then the next question is, okay, well, if I have a gas that's at non-ideal conditions, I obviously can't use the ideal gas law or any of the other equations to calculate pressure, volume, and temperature. What equation do we use? That is where the van der Waals equation comes into play. Van der Waal, named after the Dutch scientist who helped to derive it. You're going to hear van der Waal, that name again, when we talk about intermolecular forces later on in the course. He derived an equation that looks pretty similar to PV equals nRT, right? You see a lot of similar variables. You see nRT over here, you see a P here and a V here. Essentially, what this van der Waals equation does is it adds two correction factors that are needed for non-ideal gases. This one correction factor corrects for interactive attractions or intermolecular forces, and one corrects for gas volume, using these constants A and B that are specific to the gas molecule being studied. So this van der Waals equation is not one that you need to memorize. I will give it to you on the exam. But you should be able to manipulate it to solve for a particular variable. In this next example, we're going to do pressure. And you should also know that you use the van der Waals equation for non-ideal gas conditions. And in the problem, I will specifically tell you it's a non-ideal gas conditions, and you'll know then to use the van der Waals equation. There's an example, there's a problem in MindTap you need to do with van der Waals equation, and we're going to do an example now. So let's say I have a certain mole amount of chlorine gas at a certain volume and a certain temperature, and I know that under ideal conditions, the pressure would be 10 atmosphere. I'm going to use the van der Waals equation to see what the pressure is under non-ideal conditions. And so we're going to do that example here, have that same problem. Here I have van der Waals equation. When you have to do this on MindTap, you will be given the associated A and B constants for the particular substance of interest. The A and B constants I have given you here are for chlorine. You see they have really funky units because of how they are derived and measured. But using those values, getting my pen, and using the appropriate volume, temperature in Kelvin, and mole values, I can solve this equation. I can solve van der Waals equation for P. First thing I need to do is a little bit of algebra. I need to get this V minus NB term to the other side. So I need to divide both sides by V minus NB. And then I need to subtract both sides by this AN squared divided by V squared term. So doing those two algebraic processes, van der Waals equation devolves into this to solve for P, for pressure. I'm now at a point where I can input the appropriate data from the problem and the constants. You see a lot of weird units here, but when you look at the units canceling, there's no atmosphere that cancels. Everything else cancels. My liter squared. Make sure, so that unit is squared. You don't square the 6.49. You do square the 10, and you do square the 22.21. But you get something that's in atmospheres, which is great. And so under non-ideal conditions, the pressure of this chlorine gas is 9.03 atmospheres. So you do not need to memorize van der Waals equation, but you do need to know how to use it and when to use it, which is under non-ideal conditions, species at low temperatures and high pressures. You should know how to solve it for particular pressure, at a particular pressure for a particular species under non-ideal conditions.